Hello and welcome to this Isaac Physics online tutorial about the vectors problem sheet from our vectors workshops which we have done around the country. My name is Michael Conterio and I'll be your tutor for today, and I'll be sharing my screen with you so that you'll be able to see my workings as I go through some of the details about vectors and about some of the questions from the problem sheet. If you're not logged into Isaac Physics and you're watching this live, I suggest that you log in, and then you can use the box below the video on the Isaac Physics on the event page for this event. And then you can send me messages and I will try and cover what you've asked in the Hangout, in the video. But do be aware that that takes a moment to reach me, so I might not immediately reply to you, but I will come back and I will cover your point. So do hang around for that. So what I'm going to do is I'm just going to switch over onto, so I'm sharing my workspace with you. And I am going to go through a few things. One thing that I'm going to start off by going through is kind of looking at components of a vector and what we're doing with the dot product, because that's something which I found that some people occasionally have difficulties with. So I'm going to draw two vectors. And these were starting from the same point with an angle theta between them. And I'm also just going to draw dashed lines just showing the direction there. Okay, and let me also put on some axes, keeping this as my origin point. Should have drawn these on first. So got my y and x there. And let's give these vectors names. Let's call this one R1 and this one R2. Okay, so that's theta between them. I'm now also going to say that this angle here, I'm going to call theta 2. And I'm also going to say theta 1 is theta 2 plus theta. So theta 1 is the angle from the x-axis all the way up to R1. And so what we can do is we can say take R1 and we can write it in terms of the two components. So we've got R1 equals let's just decompose that into x1 and y1. So what I'm saying here is if we take just that R1, we can split that up into two vectors like this, a right angle between those two vectors. And then all we've got here is a right angle triangle, so we can use trigonometry in order to work out these two things. So if I take the squares of the sides, I can say that the magnitude of R1 squared is the magnitude of x squared plus the magnitude of y squared. And if I then do this in terms of angle theta 1, you can say that the magnitude of x1 is the magnitude of R1 times by cos theta, and similarly y1 equals R1 sine theta. If you're having trouble seeing that, imagine rearranging sine theta 1. So sine theta 1 is opposite over hypotenuse. And of course, we can also square both of these and add them together. So we get x1 squared plus y1 squared equals r1 squared cos squared theta 1 plus r2 squared sine, so r1 squared, yeah, all of these are 1s and theta 1 sine squared, sine squared theta 1. And since cos squared, which is equal to r1 squared sine squared theta plus cos squared theta, and this has to be equal to 1. So we've just recovered this identity that we had from Pythagoras. So what I'm going to do is I am going to actually, I should have picked something up to copy. So if I just, no, let's try again. Fix this on here, and then I'm going to work it. I'm going to leave that there so I don't lose it again. Here we go. That's better. So now let's think about what we're doing when we're taking dot products. So if we again have that r1 equals x1 plus y1, let's imagine taking the dot product of that with itself. So r1 dotted with r1, and we can just do that by expanding out these brackets. So we have x1 dot x1 plus y1 dot x1 plus x1 dot y1 plus y1 dot y1. But we also know that A dotted with B gives you the magnitude of A multiplied by the magnitude of B by the angle between them. And if you're multiplying, if you're dotting something with itself, then obviously theta is 0, cos theta is 1. So for this x1 squared, we just get this one dot x1 gives us x1 squared. But when we're dotting these y and x vectors, the angle between them is 90 degrees, which means our cos theta is 0. So plus 0 plus 0, y1 squared, x1 squared plus y1 squared. And so if we are doing something in terms of x and y, then we can just we're just multiplying the components together there, actually, and summing those. And yes, if we take instead r1 dot r2, so we have x1 plus y1 dotted with x2 y2. Then we have x1 dot x2 plus y1 dot x2 plus y1 dot y2 plus x1 dot y2. And once again, these go to 0. These are both 0. And so, and these have no angle between them because these are both in the x direction, these are both in the y direction. So we end up with x1, x2 plus y1, y2. And it doesn't actually have to be the x and y axes, so long as you're you're taking components which are all mutually orthogonal, so they're all at right angles to each other. It doesn't matter. You can do this in 3 dimensions, say the X, Y, and Z coordinates. This will be another way that you can break down your dot products, and this is useful particularly in question 8. Sorry, pardon me, question 9. And also when we move on to exercise 11 as well. So those are all useful there. But this idea of resolving into components is useful for the projectile questions, like question exercise 10 as well. So I'll just go over that one as well. So exercise 10 says a projectile is fired horizontally off a table at 4 meters per second. It falls towards the ground with an acceleration of 10 meters per second squared. Calculate the magnitude and direction of the velocity at times t equals 1 second, 2 seconds, 3 seconds, 4 seconds. So the important thing here is that we have our acceleration vector down, and our magnitude of that is 10 meters per second squared. And I'm going to just define my positive axes here, because we're going to have something falling. Then it makes sense to have my y direction being positive downwards. So we can then, what we also can say is horizontally we have no acceleration. So the horizontal component of the velocity is constant. Right, so now t equals 0, t equals 1. I'm going to call that t1. 1 second, t2 equals 2 seconds, t3 equals 3 seconds, and so on and so forth. So we start off with our horizontal, which I'm going to call v0. At time t equals 1 second, we know that we're going to still have that same horizontal component of magnitude v0. But we're also going to have a vertical component. And it started off with no velocity in that direction. So vertically, u equals 0, v equals u plus a, t equals 0 plus gt. So this component must be equal to gt1, giving us our vector velocity v1. And again, at 2 seconds, we'll still have our v0. This time, our vertical component is doubled. And so on and so forth. Part B of the question asks, how is the velocity related to the flight path of the projectile through the air? And the velocity is the rate of change of displacement of the particle and is always a tangent to the parabola, which is the projectile motion. So in order to work out the projectile motion, we can say horizontally no acceleration, so horizontally x equals v0 times t. So these are all just distances here. And then vertically, we have to use a different equation of motion. We have to use s, or which is in this case s equals ut plus a half a t squared. And so we get our axis is y, our u in this direction is 0, and our acceleration is g. Now we can actually combine these two equations by rewriting the first one as t equals x over v naught. So then we get y equals half g x squared over v naught squared. And this will give us our equation linking y and x. Okay, moving on to our final bit of this hangout. We're going to look briefly at exercise 12. A projectile is thrown at an angle of 30 degrees above the horizontal from the top of the cliff. It hits the level ground below at an angle of 60 degrees above the horizontal. If it is in the air for 20 seconds, how far from the foot of the cliff does it hit the ground? Use g equals 9.81 meters per second squared. So draw the cliff. Ooh. Hang on. There's my cliff. All starts at the top. All ends some other time. Call this the height of the cliff. And we'll call this the range of the cliff. Let's call this S in the X direction. There we go. And we know that we start with some U. We don't know what that is, but we do know that it starts at theta naught. And then finally, when it hits the ground, we know that it hits the ground at an angle of theta 2. It says above the horizontal, so I'll actually draw it that way. Call that, actually call it theta 1. So this initial velocity here, we've got initial components. U, x, u, y. And then we've got this final velocity. Important thing to note here, directions of ux, uy and vy are different. So it's important for you to decide which way you're going to define positive y direction to be. And we've got our acceleration of g in that direction. So it's up to you whether you say y is positive going upwards, and then your acceleration is in the y direction is minus g, or you can say that downwards is positive and your acceleration in that direction is plus g. And the other thing to remember is that these components are the same because we've not got any acceleration in the x direction. So there are a bunch of different ways to solve this. One thing to do is you can, that's a very bad drawing, but you can split up going upwards and downwards, or you can write everything in terms of h and sx and try and solve that way. It's really up to you. Well, basically, you're just using your equations of motion and these two angles, which I should have drawn in here as well. So that's theta naught, and that there is theta 1. Okay, so that's kind of a quick tour of some of the questions and some of the concepts that you'll need to solve some of the later questions in there. I hope that's been useful for you. If you have any more questions, you can go to the Contact Us page on Isaac Physics, and I will get directly back to you, or we might try and set up another one of these online tutorials that you'll be able to go to, ask your question, and follow along my work in there. So thank you very much. I hope you enjoyed using this. I do suggest using the rest of the site. There's lots of questions which your new knowledge of vectors will be very useful for. If you go to isaacphysics.org and go to the homepage, then if you click on questions at the very top, you will actually get access to a filter, which has got lots of different things there. Let's see if I can just share this with you. So yeah, depending on how full your screen is, you may get this filter more like that. But you can select particular areas of physics, choose your level. So AS is kind of levels 2 to 3, A2 is levels 4 and 5. 1 is kind of a bit more, or if you're pre-AS level, and 6 is basically anything that could be post A level. So that could be anything from just a little bit harder to university level stuff. But again, we've tried to design it so that you'll at least be able to try and get a bit of your teeth into that. And then you just go down and you'll have your set of questions in whatever topics you picked. Do go down there. There are hints and everything on lots of those. And good luck with them. Thank you very much. And I hope you enjoy carrying on to use Isaac Physics. Bye-bye.